start talking.
I just felt there's been lots of other people on this one.
There's a reef.
That was subtle.
I don't have to be subtle with you.
That's fair. So, go ahead, Louis.
Okay, so like for example, I guess that reasoning, like I know which one's the strongest nucleophile, but like the reasoning behind it, we all kept on getting tripped up about.
You mean so when asked to pick a nucleophile, you guys picked crazy difficult ones?
Yeah, well, or like, well, actually, I don't know what you mean by that. Like, what do you mean?
Can you rank it easily?
Like the nucleophile was crazy difficult, or that?
Yeah.
Well,
So when asked to provide an example of the structure, you guys started going off and picking all sorts of random crazy objects instead of trying to go as simple as possible?
You said that we needed something organic.
Yeah.
yeah.
And then with the emphasis in lab, there we go.
Okay. Well, I'm not saying what you picked was necessarily bad. Okay. What I'm saying is, given the option to pick something simple, you made it complicated.
Yeah, but simple doesn't always get it done.
If life was simple, everybody would be doing it.
That's very...
Done.
Okay.
You have the potential to make things simple, and you're trying to make them complicated. You're getting lost in these busy structures. What is a nucleophile? An electron source. Okay. It had to be negative, so that's good. We're acknowledging negative charges with our structures. Our bases had to be negative. Didn't have to be negative, right? But negative. Our electrophiles, we had to see positives. Our acids, we had to see positive hydrogens. So you have that potential, but then when asked to provide a structure, you're exploding the structure beyond reason. Right? You don't have to make it more challenging than it already is. Right? Methoxide, fantastic. Right? Keeping it relatively simple. It's still organic. We've got a negative oxygen. We've got a carbon. Cool. Does that work as a nucleophile? Yes. Right? The blue structure kind of underneath, or well, just the blue structure for our nucleophile. Again, negative oxygen. Right? That's two. That could work. What's the difference in nucleophilic character between those? Between the blue and the black. That's an observation. And I don't want to rip on you for volunteering. That was good. You volunteered something on that. But I could argue it's also blue and black.
Okay,
So, carry on.
they're both oxygens. There's no. Ask your question again.
Rank the difference between those. You said primary versus secondary. Okay, what?
Charge is the same, size is the same. Meter of resonance, charge size of reduction. That's the next one I had to look at.
Okay.
Okay, so one has more, I guess you could call this
Carbons.
more carbons that can donate into it, but that's more of a positive charge.
Yeah, it doesn't seem to make much of a difference. Okay.
I think that because there's a negative on that oxygen, it would have a partial positive on the carbon, and so we could kind of look at carbocation stability, I think, for that.
What do those structures represent? Nucleophiles. Do I care about the carbocation?
I guess not.
What I care about is that negative oxygen. After that, like, we don't really have any difference. So how would you differentiate which one's the stronger nucleophile? What's that? Okay, we could go to lab. What would he compare that nucleophile to? Okay, so we could bring in an electrophile. What else competes? What other things are electron givers? Bases are electron givers. Is that going to now come in and potentially give us a clue as to which one's a better nucleophile? Yeah? Why? What do bases do? Accept protons by donating electrons. Where are the protons? Where are the hydrogens? Okay, bring in carbons, fair game. Where are the hydrogens relative to the carbons? They're on the outside. So if I'm looking at a base, I'm reacting with hydrogens on the outside. If I want this to be a nucleophile, do I want it to react with the hydrogens? No, I don't. I want it to be able to get in to react with the carbons, the not hydrogens. Why would that matter? One has a more steric hindrance effect that can back into that. So when we go through that ranking of charge size electronegativity, you're right. You're like, dang, you're fishing at straws because you don't know what's going on, because where's that difference? In that oh crap kind of thing. Okay? You're now looking at a steric effect within that, and that's a really hard thing to nuance. That's okay. But that's where you're shifting to. Okay? Maybe if we pick different structures, we could work our way through and limit some of those potential systems. Okay? With a lot of the stuff drawn up here, we got a couple cases where we're bringing in carbonyls, which is great. We've got electrophiles showing up for carbonyls, and we've got our acids showing up for carbonyls. Nucleophile kind of brought in the carbonyls, but I think kind of secondarily. Okay? So you're looking at how the carbonyl affects that chemistry. Why are you looking at carbonyls? That's what we're studying in class. Okay. Start layering in esters, acid derivatives is part of what we're looking at. Let's look at the reactivity of the esters. What are all those possible chemistries? Because guess what you have to do within this unit? You have to look at that ester chemistry. Okay? You have to identify, do we have acids? Do we have bases? Do we have nucleophiles? Do we have electrophiles within that structure? You can compartmentalize. Okay? You should compartmentalize. That can help you simplify your process. Okay? If you're just spewing random things, okay, I can get that because it's overwhelming. Try to zero in and focus on what the functionality is that you're looking at, what we're talking about, and see how that applies to those definitions. Because that's going to allow you to now compartmentalize and say, oh, I know I'm making a new carbon-carbon bond. To make a new carbon-carbon bond, I need a positive and a negative. Well, dang, how do I get a negative carbon? We could go through and run Grignard reagents. Or if I had an acidic hydrogen, I could remove an acidic hydrogen, giving me a negative carbon. And I can now use those definitions to help me predict some of that chemistry. That's the point of using the definitions. Okay? And you don't have to do that. Ish. Okay? The other option is you memorize all of the reagents. Name a reagent from this week. That's a problem. Okay, that's hard. Dude, I just studied it this week. I don't know. Name a reagent from last week. The week before that. The week before that. Okay? If you're struggling to pull up those reagents, you aren't memorizing it, and you're also not looking at the definitions. All you're doing is constantly digging yourself a hole and then trying to dig your way out of it. That's the problem. You have to pick something. If I want to memorize reagents, then when I ask what are the reagents, here they all are because I've memorized them. Okay. I don't like that. Full disclosure, I think that's a horrible method. Because what's going to happen in a week? you're going to forget all the reagents. Okay? Never mind the fact that you're going to move into a future class and those reagents aren't going to be useful because most of you, aren't going to become organic chemists. Don't care about chemistry. What you care about is how chemistry applies to that area. That application is what the hell are the definitions and how can I look at those molecules to say, oh, that's what this is doing, that's what this is doing. And you can build out those structures. That's the useful part. That's why we've spent this semester, what are we, week 13? 13 weeks doing exactly that. So that when I ask, what are the definitions and representative structures, it should be a very quick, easy thing. Yes, this is what we're looking at. Here's a structure. Okay? Pulling from lab is fine. You've been working with lab. Okay. But admittedly, lab is going to be more complex stuff. Because we're trying to make it interesting in lab, not just white powders. Okay? Not that white powders can't be interesting, but like sugar, you put it in your coffee. Okay? It's still organic. So what we're trying to do is build on those processes. That's what you want to see and how you want to navigate. Okay? To these definitions, can I just memorize my way out and not have to worry about these definitions ever again? You can-ish, except that you have selected through either choice or just that's the only option left, an instructor that insists that you know those definitions. Right? Which means those definitions are going to be used again and again and again and again, and you either choose to ignore that information, in which case you will lose questions, but your hope is that I've also weighted the exams enough that you could just memorize your way out as well. Make sense? You've got to find that balance. Okay? Next question. That's how I feel too. Yeah.
Maybe you can do a multi-step synthesis, since I think after exam 2 you said you want to do those.
I hate to say it, but no. There's too many steps that have to move with that. If I ask the class what are the reagents and there's silence, synthesis is not the route we need to take. Okay? Because all that's going to be is me telling you the answer. I can tell you the answer till I'm blue in the face. It's not going to help. No, me anything. We've got a practice exam open. I've got lecture slides open as well. I don't know what that thing is.
The retake.
The retake, sure.
I really wanted to look at like F or G.
Like 22?
Yeah, I got it. F or G, whichever one you.
Yeah.
Are those okay?
Yeah.
Also, I feel like if we did this style of learning in the beginning of class, I would have learned much better. I want to
No,
say
you're
that
fine.
because I feel terrible that we're doing so bad, but I feel like this is much better. More hands-on.
All this hands-on approach has done is pointed out that you don't know at this point, which is okay, but beginning is the same approach. Right? And theoretically, if we look at the approach to lecture, it's been, what are your questions? So that we can hands-on approach our way through that question, and you're telling me what to do. Okay, so we could switch it up. There's 2 questions. What do you see? The one on the left sucks, okay. It's good to get it out. Okay, we have a carbonyl. What does that mean?
Are we starting with the left or the right?
Left.
Fair point. We'll start with the left.
What was a positive charge electrophilic site for the oxygen?
How do you know that?
Because the oxygen
the oxygen gets a negative charge, and then makes the positive charge negative.
You mean if you do resonance, we can see that our oxygen is negative and our carbon is positive. So the resonance helps us to predict that chemistry. Yes. Hi.
Reason I know that's memorization.
Cool. So there we go. We see BH4 and we immediately know that that's hydride. There are approaches to that. One of the easiest approaches is that I just memorized it. That's fair. Okay? But that's calling out the chemistry behind it. Cool.
I think DTO is just the solvent, isn't it?
It's just water.
It's just water.
This question's not. We could, it is a solvent. Okay. So we've got an H minus, we've got a positive and a negative. What should you do? Okay, have the H minus attack the positive. Okay, be like, I don't like mechanisms. Okay, fine, let's not draw a mechanism. I need to stabilize a negative. What do I need to stabilize a negative? Real generic. What do I need to stabilize a negative? Positive. Which means what you now need to do is look through the rest of the system and see where do you see positives. Well, our BH4 you said was H minus. We theoretically have a positive with another molecule of the other thing. We're now creating that oxygen-carbon bond. Like that's, I mean, a distinct possibility. Okay, so the suggestion there is that we could do this. Does everybody see what I'm trying to say there? You're not seeing it? You don't have to. So what we're saying is that this negative sees a second molecule. That negative comes in and attacks the positive, breaks open the pi bond. So we've got our negative structure is the bottom one. Guess we can show it in blue. It goes up and attacks second molecule. Does that make a little more sense? See the pieces now? What did that generate?
Another negative.
Another negative. Did that fix our problem? What does that mean? There's a distinct possibility that that's not particularly good. We still have negative. Our product should theoretically end neutral.
And it doesn't work because you're breaking octet.
We're not breaking octet
Where'd the
because
hydrogen go?
the hydrogen's still
Blue
there.
or red?
The hydrogen didn't leave, it was implied.
Oh, it was on a different structure. Oh, okay,
Yep.
I see. Sorry.
Okay. Possibility. Okay. We found a positive. We connect to the positive and like, that's another negative. If I just do this forever, seems a little bit weird. Okay. Mike's rude, but maybe he's not that rude. Is there another positive somewhere else?
We can use D2.
What do you mean?
Well, like, if it acts as H2O, we can get, it would be like H plus and OH minus, and then we can get D plus and DO minus.
I don't know what deuterium is. I don't know that deuterium is an H.
Well, I know, it just looks like H2O, so I take an example.
Do better.
The oxygen, if the D got removed, then the oxygen would be stabilized because it's electronegative. But it's oxygen.
That word is kind of important. Talks about the electronegativity of the oxygen. Oxygen's the second most electronegative element on the periodic table, which means where do you think those electrons are spending their time? Over on the oxygen, which means the oxygen carries a negative charge and the deuterium, or the D, would carry a positive charge. What was I looking for?
Positive charge.
Hmm.
There you go.
I don't know what the hell D is, but I know it's positive. Let's hook that up, break that bond, and I would get still don't know what D is, but did I align my charges? Did I fix this never-ending negative problem that I was going to have if we reacted it the other way?
Yes.
Huh. maybe if I track those differences in electronegativity, I could start to come up with these predictions, even if I've never seen it before. That's literally the point of looking at our definitions and applying the same fundamental rules. Okay? That's the goal. Okay? Should you have seen D before? Yes. It showed up in a couple different places. I believe this particular question showed up not only on the exam 2, okay, but now it's showing up on the retake. You knew exam 2 didn't go well. If you were like, what the hell was D on exam 2, maybe a good thing would have been to
Study what it is.
look up what it was, particularly because you were told that you were going to have a retake that was going to follow up on it. If I know a weakness, what should I do?
Remedy.
I should fix that weakness. If I don't know the definitions right now, I better fix that weakness so that I can build this up.
Wait, what happened in the part, so we added that, or that hydrogen came out, and then that arrow pointing down, what happened there? That long structure, yeah.
This one down there.
Yeah, so what was the problem?
What we went through there is we said we've got this negative oxygen. We do have a positive in our carbonyl. Why not hook those up? Let's see what happens. If we hook those up, what happens? That's that product down below. That gets us a negative oxygen. Why did we have a problem? We had a negative oxygen.
So, like,
Did our solution fix anything? No.
So, like, we didn't really even have to show that part, or we did to get to
Did that have anything to do with getting to the neutral structure? No. Okay. What that was is I've got positives and negatives. Let's try and jam them together and see if it works. Okay. You should be taking positives and negatives for every single reaction and jamming them together and seeing if it works. Okay? See if it looks like it's getting better. If it's not getting better, there are scenarios where we now move into kind of content areas. Maybe if we do another step after that or another step after that. Okay? Looking at this one, what's our other step after that to stabilize that negative? It's still back to that positive. It's still back to that positive. Right? There isn't a nice thing to stabilize that. Okay? So it runs into, unfortunately, a dead end. If we just react out that positive D, we end it real fast.
Is it possible through like a similar mechanism to create like an ether polymer like that, or is
Yes.
It... Oh,
Yes. Right. And to that end of dealing with polymers, don't. Just don't. Possible, yes. It's not worth your trouble. Why? Jerk.
So you wanted our product to have a D bonded to the oxygen and not an H.
What charge was the
It's
H in
deuterium.
solution?
Well, you had your borons that were the hydrides and the bonded to the boron. But
How many times is
deuterium is-
boron bonded to our structures in our answers? Okay.
But I thought deuterium was just depleted water.
Depleted water?
Depleted, I don't know.
If
that's
I,
what
I would
thought.
actually push it the other direction. It's enriched water to get the deuterium.
Enriched water? So
Yeah.
what is enriched water? So
You have-
DTO is
You
just-
have heavy water. You have more deuterium in it. So what is the difference between deuterium and hydrogen?
it's the neutron.
In a Chem 130 class, for the record, I talk about it between deuterium and hydrogen.
I took that class. I don't know.
I wasn't intentionally, I mean, I was totally intentionally
Yeah,
throwing
you-
salt,
I think don't
attempting
say
to be
words,
anonymous,
sure.
but what is the difference between deuterium and hydrogen? What is hydrogen? It is one proton. What is deuterium?
2? 3?
2 protons would be helium, so it ain't 2 protons, because otherwise we'd call it He.
One proton, one neutron.
1 proton and 1 neutron. How many subatomic particles are in it?
2.
2. What's another name for, I don't know, how about 2 people singing together? There's deuterium. That's where it comes from.
I actually don't.
Right? Why did hydrogen not have a neutron?
Because it's stable like that.
Why do you need neutrons?
Stabilize bigger.
To stabilize the positive charges repelling away from each other. Hydrogen doesn't need it because there's no repulsive force within its nucleus. Right? Which is why we see hydrogen with one proton. Right? Why do we use deuterium? Deuterium changes the mass. Can we see a mass effect? Yeah, where do we see the mass effect? For the record, you can see it in chemical reactions. That's way harder than you want to do. Don't do that. Where do you see a mass effect?
You see it in spectroscopy.
You would see it in, I don't know, mass spectroscopy. Yep, that's where it shows up. Okay, you would see a deuterium effect within that. So you could start to see how deuterium interacted and how it manifested through a chemical reaction by studying the products in mass spec. Neither here nor there. Well, I mean, spitting facts, I guess. Been told I'm too old to say things like that.
No, it's okay. You pull it off.
Yeah, you're hip with the kids.
Okay, so what happens here? And actually, let's, before we even look at that previous reaction, I know it's not up there anymore. Where's that coming from? Exam 2, because that content was Exam 2 content. This isn't Exam 2 content. Okay? This is different than Exam 2 content. Why? That atom is not a carbon or a hydrogen, it's a chlorine, and that chlorine could act as a leaving group. If we change the identity of that atom, that changes some of our chemistries. We now have to understand how that chemistry changes. Okay? Well, how does it change? What is the primary chemistry when we look at this structure? What is the primary chemistry when we look at this structure? Okay? You're referencing that positive carbon again. Why would that carbon be positively charged? Okay? So we could reference the leaving group. Not bad. I'm okay with that. Do better. Oxygen's electronegative. Also, not bad. That's the exact example we used on the previous one. Do better. No.
It's both the carbonyl and the leaving group.
Nope. Do better. Well, I mean, yes, but do better. That's the same thing. Do better.
The chlorine is an electron withdrawing group.
Already addressed that. Chlorine's a good withdrawing group. Yes. The oxygen's electronegative. Yes. Both of those make that carbon positive. Why is that my primary focus for my chemistry? Yeah, we've been focusing on the carbonyl and we've been looking at its reactivity. Okay? We might even go through and say draw a resonance structure. Maybe this helps as a potential hint. If we draw the resonance structure, what are we doing when we draw that resonance structure? How did we get here? I think I heard it. What'd you just say? I have no idea who said it. I just heard words. Not good enough. I didn't remove electrons because the electrons are still in the structure. Okay, moved. Okay, fair. You moved electrons. We moved the what? The pi bond. Why is the pi bond a special focus for us?
The electrons in the pi bond are easily movable.
Why are they easily movable?
Resonance.
They're in p orbitals. Why does that matter? I mean, you're still right. Yes, the p orbitals don't directly overlap. Every other bond is involving sigma orbitals, which have a direct overlap. Why does that, again, draw us back to the p orbitals? They're higher in energy. Let's break the bond that is the highest in energy first. That's what we do in all of our chemical reactions. We break the highest energy bond. Right? So that carbon being positive, yes, it is partially positive for all the reasons you're addressing. Okay? If we look at the resonance, we're moving pi electrons because the pi electrons are higher in energy. That helps draw even more crystal focus on that reactivity. So the pi bond needs to break. If that pi bond breaks, what happens? Well, I'd get a positive carbon and a negative oxygen. Which of those two is the most problematic for me? Positive carbon. And of course, we got to follow it up with why.
I just said so. The oxygen can stabilize the negative. Well, I mean, I guess the carbon.
So we could say, well, the oxygen stabilizes negative.
No, I'm gonna change my answer. Carbon dioctet.
Ah, there it is. If we go all the way back to Gen Chem 1 and we look at Lewis structure rules, how we build molecules, the best structures have complete octets. That carbon is missing an octet. That's insanely bad. I need to fix that first and foremost. How do I fix it?
Negative. Well, I'm not negative.
I need a negative. Do I have a negative?
We can get one.
Yeah. I did.
We're gonna act like the H2O.
H2O. Is that negative?
It is for us. It's got electrons, so
There's a good switch to this definition. It's not that I need a negative, it's that I need electrons. Okay? I need something to share electrons with a positive carbon. I need a nucleophile. That nucleophile should have electrons to give. Water has electrons to give. Water could go through and share those electrons. We could get our product out of that. The ring, of course, does nothing. Not, of course, necessarily, but just drawing it ugly. Now what?
got it. Sounds possible. I don't know.
Oxygen is gonna donate electron or lone pairs, and that's gonna kick the chlorine off.
Okay. So when you say the oxygen's going to donate electrons,
It's gonna want
this oxygen's going to donate electrons?
Oh, wait.
Yeah, sorry.
No, you don't have to
No,
apologize.
No, I know.
Your words just weren't clear enough to make me understand what you were trying to say, because I'm a prick. Okay. If we adjust it, okay, the negative oxygen should share electrons. Lovely. What do you want to have happen? You said it.
Well, you're gonna have the chlorine pop off. And
I
then
want
it's gonna-
pause. Chlorine to pop off, which means the leaving group would be okay. When those electrons come back down, that red arrow, we want to fix the exceeded octet. We'll fix the exceeded octet by kicking out a leaving group. We've got chlorine as a potential leaving group. We also have water. We also have but don't draw that, Mike. It's wrong. Why is it wrong? Why do I not want the phenyl coming out?
Negative carbon. Straight.
So negative carbons are unstable. We could never form them in our chemical reaction.
Well, not never. Come on,
We'd
Mike.
end up going backwards.
You just said you were right.
Well, I'm going to keep digging.
I didn't say never.
So make it better.
Wouldn't happen here. It's not better
So
than
stable.
the negative oxygen. Caria.
When we look at our chemical, those three options are all perfectly valid options to consider. You should be excluding some. I'm going to bet the vast majority of you exclude the carbon structure. That's good instinct, but you need to know why your instinct is good. So push on your instincts. That's a negative carbon versus negative chlorine. Which one can stabilize those electrons better?
It's chlorine.
Chlorine. Why?
Or
Electronegative, which means, actually, it's not electronegativity. Size becomes the important part. Size of the chlorine versus the carbon, not the whole ring, just the atom where the charge is located. That means that was a bad idea. Fair. I'm a jerk. I was wrong.
Green's bad too. Yeah, what Austin said.
Which is the better leaving group? Water or chloride? Water, because charge. I love your idea. You've got the long game in mind, but your short game is crap.
Yeah.
Okay? So if you want that chlorine to leave, water's the preferential leaving group, you go backwards. Okay? So you focused on that negative oxygen. That's phenomenal. Good instincts. But you have to ensure your instincts are supported by next step thoughts. Okay? So I don't want those electrons to come back down, because if they do, I go backwards. I don't want to go backwards. I want to go forwards. So what do? Water was a really good leaving group. How about let's make it not a good leaving group? Water was a good leaving group because the oxygen was positively charged. If I fix that, I could have the electrons go back to the oxygen, taking me to a new structure. I've not addressed my negative oxygen, but I have addressed my positive oxygen. Both of those were bad, unstable things because they were both charged. Okay? You picked one, and in the case of a mechanism, you were wrong. That's okay. In the case of predict the product, you were right. Okay? Now what happens is we can go back and say, well, those electrons come back down. We again run into the scenario where we get three possible leaving groups. We get negative carbon, negative oxygen, negative chlorine. They're now all negatively charged, so I can ignore charge and I can move next to size. And I'm comparing chlorine to oxygen to carbon. Chlorine's the biggest. That's my best bet to eject the electrons. There we go. Damn, that was a lot of work. There's no way I could be expected to learn all that for an exam. You're not expected to draw all of this out during an exam. Okay? It depends on the level of question that's being asked. If I ask for a mechanism, yes. It sucks. Draw it all out. If I ask for what's the answer per the exam thing, there are two approaches. One, you start to draw it out, recognize those patterns, and go, I know water's not a good leaving group, but I don't want it to be worried about it. I'm just going to kick out the chlorine. I've got a carboxylic acid. Done. You cut a significant portion out. What's the other thing you could do? Hopefully you were good with everything that was written there because I just erased it all. Oops, bad arrow. What am I drawing? The stability ladder for our acid derivatives. If you'd memorize the stability ladder, that the acid derivative can go down to anything by just supplying the missing piece that I want to do, all you have to acknowledge is that when we look at that difference, I've got a chlorine and I've got H2O. Breaking that up, HOH, that looks an awful lot like what I'm doing is moving to that acid. I'm done. I've memorized the stability ladder. I can make that jump in a single fell swoop if I've memorized it. Did you memorize it? Okay. Again, your choices, those choices will be reflected in the exam. And I fully know that looking in the mirror can be a very scary thing. Right? But that's what the exam is trying to do. I agree. Sorry, I guess I was the only one that heard the sigh. Yes, John.
With the mechanism where the hydrogen gets taken off with the water ion, is that taken from another water molecule to make, I think, the hydronium ion?
So, and this becomes a common kind of question. This hydrogen, all we're showing as far as this mechanism goes, is that the electrons in that bond just go to the oxygen. Okay? In OChem 1, we're like, oh, we can't really do that. We have to show what picks it up. We've talked about it a few times through this semester. We generally don't care what picks it up. Okay? A base picks it up. Okay? Overall, I would argue I don't want you to get bogged down in what that base is, because there's the vast majority of cases, it's just something remotely basic there. Okay? You can push it a step further. Sometimes it's in the workup. Well, how often is the workup shown in any of the lecture content? It's shown in one case that I know of off the top of my head, just for the record. Actually, two, now that I think about it. Grignard and Gilman. Those are the only two that actually show a workup. Everything else, we don't talk about it. It's just assumed. Why they show it for those but nothing else, I have no idea. Okay? So that hydrogen could be picked up by a subsequent quenching of the reaction, which is going to cause all of this kind of secondary stuff to happen. Okay? Typically, it's picked up by a base, and you can have all sorts of mechanistic arguments over what base should be picking it up, which is why I don't like it, because one of the arguments that you can sometimes see is that, well, there's chloride floating around because we had it as a leaving group. So since it's negative, it picks up the hydrogen. And I've seen that as a mechanistic result in lots of different places. And that should scream problematic.
Let's see.
What you make is HCl. And what is HCl? Hydrochloric acid, and more particularly, it's a strong acid. It, by definition, completely dissociates back to the ions, meaning chlorine does not pick up the hydrogen. Having chloride act as a base is a really bad idea. Right? So what would be our base? We could reference water. We could have referenced the starting carbonyl compound. Okay? But that means we're drawing a massive structure. I don't want to draw that. So just write frickin' base and not worry about it. Okay? So the adding and removing of hydrogens can happen almost at will. You do have to be a little bit careful that you aren't showing charges that shouldn't be there. Okay? So if you're running under acidic conditions, don't form a negative oxygen. Because under acidic conditions, I should expect to see a whole hell of a lot of positives, because under acidic conditions, I have proton donors. I have H plus floating around in solution. There should never be a negative. If I'm under basic conditions, I've got proton acceptors, which is okay, but they're accepting positive by doing what? Donating electrons, which means I don't want to see positive charges floating around in those scenarios because I have a ton of negatives. Those negatives would immediately quench with those positives. Right? So it's again going back to those positive and negative reactivities as we propagate through our systems. Kind of, sort of?
Whatever you can, you do.
Yep, that was going to be the next one. Can I delete?
Like the stability ladder, it goes from more stable is the highest or lowest?
Highest is least stable.
Least stable. Okay.
Yeah.
Since I didn't memorize it before.
Think about a ladder. If you're climbing up the ladder, if you're at the top of the ladder, how easy is it to get to the bottom of the ladder?
Yeah.
You just fall. There you are. Okay. If you're on the bottom of the ladder, how easy is it to get to the top? Falling doesn't help.
Yeah.
Okay. So this one said rank base strength. What would be a really good place to start this question? What the hell's the definition of a base? If you're being asked to compare base strength, maybe you really want to know what a base is. I already wrote that on the front. Okay, did you look at the front of the exam where you wrote the definition? I don't know. Did you? If you did, okay, cool. Was your definition right? Okay, so you got to make sure you've got a good definition. Okay, what is our definition of base? Okay. The definition we typically run with is a proton donor. Sorry. Proton acceptor. See, it's easy to get them confused. Okay? Deciding which one's the strongest base, though, that's talking about the thing that it's reacting with. And it's reacting with the same thing, which means I can't tell a difference between the two structures using that definition. So how does it accept hydrogens? Okay? A negative charge isn't a horrible definition, except that when you go through and look at these, there's no negative charge. And that's the problem with that definition. Okay? What we want to see is electrons. So we can look at this and say, okay, which of those electrons do we think is the most relevant to be comparing?
Me missing a charge. Oh, no.
Nope, I'm not missing a charge. But thank you for making me look, because I did look.
Gotcha.
The lone pair.
The lone pair electrons. Okay. Okay. Extra kind of emphasis, we're looking at the lone pair on the exact same atom. That makes even more sense to be now making a comparison. I need to look at the ability to donate electrons. So I'm going to start looking at charge.
The same.
The same size.
The same.
Electronegativity.
The same.
Resonance. Okay, so maybe we should look at resonance a little bit. Which one do you want to look at resonance for? The second one, okay. The black dot in there is killing me. Okay, so what do we want to do? Moving the pi bond.
Well, I guess you
So it's lovely to say that moving the pi bonds tend to be higher in energy. That makes sense. Let's look at pi bonds. What are we trying to rank here? The base strength, and in particular, the base strength of the nitrogen lone pair. Should I be touching the pi bonds? No. What I should be touching, that's a weird way to ask that. I apologize. The lone pair. Okay? I can only move the lone pair from an atom to a bond, so let's go ahead and move it to a bond. What happens? I exceed the octet on that carbon. Move the pi bond. Okay? For those people being, well, why didn't you go all the way to here? Well, then I exceed the octet here, and then we go all the way over to here, and then you get this weird, like, never-ending loop cycle behind it. And that's because what you're doing is not trying to draw short resonance. You're just trying to draw all resonance. Always draw the shortest possible resonance leaps that you can. If you're going to start an atom moving to a bond, the very next bond you move should go to an atom. That keeps you the shortest distance with your resonance, and it makes sure that you don't miss any resonance when you move your structure around. So if we look at this, we have a resonance option here. Right? Evaluating whether that is good or bad is effectively a moot point. I need to start by looking at where those electrons are located. Do I have valid resonance? Yeah. Does the other one have resonance? Okay. And this is the fun one that we got to be really, really careful with. Where do I want to move those electrons, left or right? Okay, I want to move them to the left, because if I move them to the right, what happens? Not only do I exceed octet, but where are those electrons at best going to move? They would move up to there. At best, it's going to generate this weird system that's going to be very hard to kind of propagate through. Okay, so it makes more sense to move our electrons into that single bond. What happens at this carbon? Exceeds the octet, and our electrons move up there. Okay, and we could go through and draw this out, and I will, but it's a bit misleading. In looking at this resonance, do we see anything that screams a little bit weird? And that could be no, that's fine. Yeah? You see something a little weird? What do you see a little weird?
I know the nitrogen can have the two atoms like that, but I mean, there's more resonance that like works, I guess.
I'm not asking about more resonance. I'm asking, is that structure okay?
What do you mean, okay? I mean, it's a resonance structure. The same way the
Is there
other
anything
ones.
that looks weird? So your argument is that you don't really see one, even though you said
No, I
yes.
mean,
That's okay.
it's
I heard
most-
Emily first, then we'll go to John.
I don't know about,
Sorry.
I said that the thing that I'm
Yes, but I think you're referencing a conjugation that's really, really hard to see. You're technically right, and maybe it's easier for you to see it here. We'll come back to that. What were you going to say, John?
I was gonna say, it looks kind of weird for the nitrogen to have two, like, double bonds on it. I don't think that's.
Oh, what has to be
Is it firework?
So 2 double bonds is technically okay, but there's another issue there. What would its hybridization be? SP. What is the bond angle for SP? It would need to be 180 degrees. Can I take a 6-membered ring and have that be 180 degrees?
No.
We're going to run into some massive angle strain there. Okay? So that is where I would argue you should potentially see, like, this is strange. Maybe I need to look closer. And unfortunately, where do we need to look closer? Exactly what Emily was suggesting. Conjugate. What is conjugation?
It's a pi system that's linked up through resonance.
It is a pi system where we have overlapping p orbitals, which means everybody's favorite, we need to go through and look at molecular orbitals. Okay? I was going to gesture on the iPad. That was just a stupid idea. Let's just set that down. But I guess for the audio. Where are the p orbitals making this double bond? They are up and down. Okay, they're coming in and out of the plane at us. Everybody okay with that? Where must those p orbitals be?
Which ones?
Making the red pi bond.
Maybe I'm gonna be going like this.
Okay, and this is hard. We need to get the frame of reference. I don't know what this is other than potentially questionable hand gestures. This is recorded. No one knows what it was, so it's okay.
Would it be also coming at us?
Also coming at us. So if we look at this nitrogen has a p orbital involved here, right?
Yeah.
It also has a p orbital involved there. And you're saying the 2 p orbitals on that nitrogen are in the exact same space?
One's like this and one's like that.
They have to be perpendicular to each other. So if I have the p orbital coming in and out of the plane here, the p orbital making this double bond cannot be coming in and out of the plane. It must be rotated 90 degrees. Why does that matter? What happens to my conjugation? Can my electrons communicate now? No, because the electrons aren't communicating because the p orbitals do not overlap. Okay? So you are absolutely correct in saying that you lost conjugation. Mind blown that you saw it there, but that's okay. Where I would reference that conjugation goes all the way back to our starting structure. The p orbital on this nitrogen and that carbon, they're all coming in and out of the plane. Where are these electrons? Where's the lone pair electron? In the plane of the paper. Can that resonate into that pi system? No, because the orbitals don't overlap. What does that mean? No resonance. What does that mean? And this becomes the challenge. It goes back to our initial question. We're looking at the ability to donate electrons. Okay? The structure on our right does resonance. If it's moving electrons into the structure, can it donate them? Because when we talk about donating, it's donating the electrons outside the molecule. If we have resonance, the electrons are going inside the molecule. That's not good. How about this other one? Can those electrons go into the molecule? Nope. So which one's the stronger base? The left one becomes the stronger base. Because the other structure has a resonance system to stabilize it. Okay? This is setting us up for the next unit. Okay? Because what we're going to talk about in the next unit is this concept of aromaticity. Aromaticity is just resonance and overlapping p orbitals and conjugation, okay, in cyclic structures. Those definitions are things you already have control of if you acknowledge them. Cool. So it allows us to apply outwards. Real quickly, the last one. Chlorine. Was it an acid or an ester?
Oh.
It was an ester. Whoops. Actually, it wasn't even that. Said to now rank acid strength. Acid strength, we're looking at proton donors. How do we rank our proton donors?
Conjugate base.
We look at the conjugate base. So the very first thing we should go through and do would be look at our conjugate bases. Theoretically, you should acknowledge that being closer to the chlorine is a more stable conjugate base than not being next to the chlorine. So if we compared apples to apples, we could set up that kind of system. Okay? And if we go through and evaluate, our charge size, electronegativity are all ultimately going to be the same. Resonance is also going to be the same because it can resonate up into the carbonyl. The one difference is that we're looking at chlorine versus hydrogen. Chlorine being more electronegative does what? Induction. Draws the electrons into the molecule. If the electrons are drawn into the molecule, what does that do to the negative? It makes it more stable, or a smaller negative if you wanted to go that direction. And if it is a more stable structure as a conjugate base, what does that mean about the acid? That one's the stronger acid. Sorry, bro.
That's like exactly what I put.
Okay? But that's the argument that you run through with that. And if you want to challenge, it's okay. You can bring it back to me. I'll take a look at it.
I did put it was the chlorine reduction.